I can't blame you though, you gotta try, right? If it was Tuesday, there'd be even more stuff on it, so I don't want to try on Tuesday. So Monday, there's a quiz. Let's see if I can remember what I said was wrong. I'm gonna ask you. Shit, that spot. 11, yeah, sounds familiar. 11:3 to 11:6. Or 11:8. Yeah, even better. That's already a lot of stuff. I like it. And just remember that you've got your homework sheets. One of these sections wasn't even in our curriculum in the first place. I think it was 11:4. And 11:5 I made extra credit, or vice versa. So it's really 11:3, 11:6, 11:7, 11:8. So you guys, I'm sorry. It's me. It's my day that I'm having. That's causing that. You have to be a part of my day, I'm sorry. We either roast to death or we hear the horn. Maybe. It's a little warm in here.
I like it.
Huh?
It's because of
You're over budget.
They shut up downstairs.
Huh?
They shut up anyway.
Yes, exactly. Good. Just in time. All right, so any questions from homework? I was hoping maybe that was for something. Even just how the shit do you do anything in section 11.8 or something? You got something?
No.
No. Okay. All right. How you guys doing? You guys are doing okay? So you always, everybody knows my office hours, right? On the syllabus of my office hours. I'm in the office more often than that. Right. If you're relatively new to college, you got to start getting used to using those. Holy shit. So number one, you get your questions answered. Number two, the professor knows you a little bit better, which is almost always a good thing, right? And I don't know what else. Number three, you can be more open about anything that's going on in your life. I can't treat any student differently than others, but I can try to come up with strategies in certain situations. I've been in situations where I was doing too much, I had medical problems, I've been in all these situations myself, so I could try to figure out something. But I do appreciate you're here. There are quite a few people not here at the moment, but I'm still going to take a video because I'm not that big of an asshole yet. Part of me wishes I was. All right, so there's no questions from homework. Let's kind of review what we did yesterday a bit. See if any of my markers are working. Hey, all right. We did some old stuff. Let me focus on what was new. Inverses. Start. So this idea of finding an opposite function. So if I have a really basic function, if I have a function that doubles something, the opposite function should be what? If I have a function that doubles something, the opposite should cut it in half. I love it. So on the real surface of it, you can figure out basic inverses without even doing any work. But when you start having a lot of things happening, we have wanted to develop a process. So let me start with the algebraic. I'm going to kind of do what we did last time backwards. We'll start with the algebraic approach to finding. So if I'm given an f of x, let's see, what do you got, Jeff? Let's do, Anybody remember the symbol for the inverse function, the opposite function? Yeah, it's such a bad symbol. I wish. So it would say find this. Part of me kind of appreciates, a very, very small part of me, appreciates that somebody might just put 1 over this. And you might see why they would think that, but I'm telling you directly again today that is not what this means. This symbol means the function that does the opposite of what this does. So let's take some guesses and see if we're right. This function has a cube in it. So I'll bet you anything my inverse has a... This function has a plus 5. I'll bet you anything my inverse has a minus 5. This function has minus 2. Okay. But it's just kind of like the order it's in and all that kind of stuff. And there are functions that are their own inverses, for example. I'll do that example in a minute. That's kind of nifty. If I just ask you, does anyone want to take a guess what function is its own inverse? Don't worry. It's a little bit freaky. It's a type we haven't really looked at too much directly, but we have seen it. So let's see, what are the steps here? What's the first step to doing this? Anybody remember what's the first step to algebraically find the inverse? Bring the y back. Oh, my markers are dying.
Switch the X and Y.
Switch the X and Y. I'm going to do this weird-ass dotted line thing just because I can't allow myself to do something that's not really algebraic. So I applied an idea. That's why I have to put that dotted line for myself. I didn't really do something algebraic to both sides. I just switched X and Y. Now if you missed yesterday, well, let me explain why this step makes sense now. What I'm going to start to do, if I try to resolve for y, I'm going to start to undo all the stuff. So I'm going to create, as I start to solve for y, I'm going to create the function that does all the opposite stuff in the opposite order. Can't be more opposite than that. That's going to be the inverse function then. So first thing would be subtract 5. Then what can I do? Cube root. And then finally, bring it up here. Add 2. So I get y equals cube root x minus 5 plus 2. All the stuff we expected it would have. So I can officially put f inverse equals this. So just to redo what we did last time. Let's see how well you're working. Okay. So what is f of 3? What's f of 3?
6.
Yeah, 3 minus 2 cubed. So 1 cubed is 1 plus 5 is 6. And I already know what this has to be. What does f inverse of 6 have to be? What must it do? F did something to 3 and made it become 6.
Oh.
F inverse is the opposite function. What is it going to do to 6?
Negative.
Take it back to 3. It's going to undo what the other dude did. Man, this guy made me sick. I'm like, all right, I'll make it 3 again. Well, let's see if it does. So I already know the answer is supposed to be 3, if we did this work correctly. Let's see. Cube root. So I'm just going to plug a 6 into the inverse function. Cube root of 1 is 1 plus 2 is, it did it. It took it back to where it was. And on one level, I hope the God, you're like, well, of course it did, Jeff. We just made the function that does all the opposite shit. So on one level, it should be sort of, yeah, that's what we just did. Maybe, hopefully, yes. All right, and then this is where I started yesterday, was graphically thinking about this. If I'm given a function, I have no good markers. If I'm given a function, let's see, you guys probably don't work it. Oh yeah, that's right. I get excited about simple things. They give me a graph of something. Let me. It's my day. It's the way it is. One student would say I deserve this because I'm such an evil person. How dare you make me not cheat? All right. Sorry, you got to work through it. Sorry. So let's see. I can't make something too crazy for us. Yeah, let me make it a little bit crazy. All right. So what am I being careful about? who remembers from yesterday's lecture, in order for this to work, in order for it to have an inverse function, what's got to be true?
Horizontal line.
Horizontal line test has to be passed. Because the whole idea of an inverse function, I like to think of it as detective. I'm able to work backwards to where I started. But if I have a function that does something like this, so it does not pass a horizontal line test, if somebody tells me the output was 5, but there's 2 places where 5 could have come from, I can't work back. I can't say for sure what the number was to begin with. So what is the main thing that an inverse function kind of does? It takes the outputs and brings them back to what they were. If there were 2 possible places where 6 could have come from, it can't do that, therefore it doesn't exist. There is no function that can do that, so we don't have an inverse function. Really, really want that to make sense. The whole idea of this is, I have an output. What was the input? In order for me to be able to answer that question definitely, I have to have a function that doesn't do this. There can't be 2 different places that it could have come from. Right? Maybe. You all see movies where like, there's this kind of mud on a shoe, and there's only one place in the world that comes from. Let's all go there. That's where he is. You guys have seen that scene somewhere, right? Well, one of us is like, well, there's 2 places, the opposite side of the earth, and we don't have time and shit. Right? So I can't, then there's no inverse function. There's no inverse mud sneaker function. Right? All right, I like that phrase. So, here's my f, here's my function. How do I get the inverse function graphed? I don't even know what the shit it is, but I do have the answers for it. What points does this function go through? Let's see if you guys can read my horrible. Right. -4, -3. 0, -2. 1, 4. 4, 5. I like it. So the inverse function has to go through what points?
The opposite.
Yeah, be really, really careful when you say that. Don't change any signs. You just mean do exactly what we did algebraically. Just take the x and y, switch them. So this goes through -4, -3. My inverse is going to have to go through -3, -4. It's going to go through -2, 0. 4, 1. 5, 4. And then what happens is kind of nifty. It's a little bit pretty. You got to admit it. So if I plot these points, -3, -4, -2, 0, 4, 1, and 5, 4. You're going to have to get right in the middle of you there, buddy. What do you guys notice? Those 2 functions, are they visually related somehow? Yes. One of them, that red one, looks like the blue one was flipped around some line. And of course, if you were here yesterday, you know what line that is. What line was it flipped through? Which is y equals x. Yeah. And again, if I switch the x and y, and visually it flips over the y equals x line, those seem to go together. Okay, I like it. So I will give you a problem where I say find the inverse, and I'll give you a function. You got to find it. Switch the x and y, resolve for y. So on that level, you should be able to attack that problem. If you get x minus 2 to the 5th power, do not multiply that out. I'm not asking you to do that. Are you with me? Yes. And I'm going to give you a graph. I'm going to give you a graph. I might ask you, why does this have an inverse? Then you have to tell me it passes the horizontal line test. And then I'll say, graph the inverse. And I'll have somebody come up and say, you didn't give me a function. And I'm like, I didn't have to. I gave you all the answers. Right? You guys with me? And you'll see these problems in the homework too. Kick ass. All right. And the final thing I want to remind you about, even without telling you what f is, what is this?
7.
Yeah, it's 7. These two kill each other. We've been doing that this whole semester. In fact, using my terminology, we've been killing so many things. So when it had a cube root of x minus 7 equals 2, what did we do? We cubed both sides. Why? Because cube is the inverse of cube root. They kill each other. Are those the only kind of functions that are inverses of each other? No. There's a ton of functions that have inverses. So whatever that function is, if I act on it with its inverse, they kill each other, freeing the dude inside. Maybe. So, and let me push it one more step. If I can write, if this is true, and the inverse exists, what can I write about the inverse? Let me see if you guys, this is pushing it a little bit. We should be able to do this. This is what we were just talking about a minute ago. If f of 2 is 4 and I know f inverse exists, what's one thing I know for sure about the inverse? Yeah, f inverse of 4 has to take it back to 2. Kick ass. So I love that that same idea holds through the 3 different ways of thinking about it. That idea guides us in every step. Okay, maybe. And to be really, really honest, I wish I could get a book that would teach this earlier. We should learn inverse functions way back when we first talked about functions, to be really honest. I hate that they kind of bring it in now and then we need it immediately. We should have already known about it. But we'll get over that, or I'll get over it. Okay. So, now we're going to take a bit of a sidestep, and then we're going to immediately come back to this inverse thing. So the sidestep we're going to take is we're going to introduce a function we've never... Oh, I promised you something and I forgot. Real quick, before I do that. How do we get the inverse of this function? What do I do? Switch x and y. How do I solve for y? Multiply by y. Divide by x. So what's the inverse function? Itself. And why does that make sense? What does this function really do? If I put a 2 in, what's the answer? So if f of x is 1 over x, what's f of 2? 1/2. What's f of 4/5? Think about this for a second. Or, a few seconds. What's that do? It's going to be 1 divided by, well, how do you divide fractions? What's 1 divided by 4/5? Flip it. So that becomes 5/4. So this function actually can be considered as the flip function. So how do you undo a flip? You flip again. That's why it's its own inverse. You guys get that? All right. You're not reacting the way that I wanted you to. I'm sorry. I remember young Jeff going, "Whoa, that's so cool!" And just to show you, you don't have to know this, but this picture looks like this. I think I've shown you this earlier this semester. I was talking about Gandalf, you will not pass. X can't be 0, right? That's why it's got this weird shit at 0. What do you notice about this relative to what we did earlier? Isn't it already, so if I flip it, doesn't it just land right back on top of itself? That's a visual showing of why it is its own inverse. It already is symmetric to that line. There are a few other functions, categories of functions that are symmetric to this line. Not many of those. It's kind of nifty when you find something that is its own inverse. It's like, whoa, neat. And then you move on. Okay, what was that about? Oh yeah. So, let me see if I can phrase this in some other way than I currently have in my head. I don't think I can. Where have we not put the variable yet? So let's think about this. We put the variable by like this. We put it like polynomial stuff. We said, well, what about on the bottom, right? And you guys didn't ask for that, but you got it anyway, right? And then we put it inside of roots, and then we did all kinds of shit with it. What am I forgetting? I'm forgetting something. That's basically everything we've done. Oh, we put it inside absolute values, right? So one definite place we have not put that thing yet is itself in the exponent. We've done x squared, we've done x cubed, we've done x to the 1/2, right? But what we haven't done is something like that. Have any of you guys ever watched horror movies or disease spreading? Like they say, the disease is spreading exponentially, or the monster is growing exponentially. This is an exponential function. Why does it make sense to call that? Because where's the zombie? I love it. Zombie outbreak. Zombie spreading exponentially. This is exponential because the variable is in the exponent. Again, math people, very creative. Variables in the exponent, let's call it exponential. It kind of makes sense. This is also known as the doubling function, and we'll see why in a minute. Let's make a table so we can figure out what the shit this thing looks like. So let's try, whenever there's a function, I don't know what it looks like. Number one, let me ask you guys, is there any number I can't raise to 2? Can I raise 2 to a negative number? Of course I can. Think about it. What's 2 to the negative 1? It just makes it flip. 2 to the negative 2 is 1 over 2 squared is 1/4. So I can put negatives in. What's 2 to the 0? 2 to the 0? 1. So I can put 0. I obviously can put positive numbers in there. So there's no problem. This guy's domain is all real numbers. Because there's no number I can't put up there. I can raise something to any number I want to.
Can you put an imaginary number?
You can, but we're not going to. I like it. In fact, I think I wore that shirt at least once with that equation that has an I. I should wear that again. It's got this funky, we haven't even talked about this symbol yet. So yes, you can have, we don't even know what that base is yet. Some of you guys might know what this is. It's sort of like pi. It'll come up very, very, very soon. There's pi. And there's I. So math people, we all geek out over this equation because it has the additive identity, it has the additive, it has the multiplicative identity, it's got complex, it's got pi, it's got e. We're like, dude, this thing has everything. Oh. Anyway. But just, give us something. What do we got? All right. So let's put a bunch of stuff in here. Normally, these are my go-to 5 numbers to put into a function just to try to figure out what this thing looks like. So go ahead and try to finish that out. Let me do the first step with you guys. So what's y going to be? It's going to be 2 to the negative 2. The negative makes it, so this is going to be 1/4. Keep going. Finish that table out. What's 2 to the negative 1? Just flip 2. 2 to the 0. 2 to the first. 2 squared. I did just say squared. Alright. So let's try to graph this sucker. Now think about this. Let me point something out. This function has an interesting aspect to it. If I put negative 3 in there, it would have been 1 over 2 cubed, 1/8. You guys with me? Negative 4 would have been another 2 on the bottom, 1/16. So when x gets really, really big negative, the result I get is smaller and smaller and smaller. You guys see that? So if I put a negative 3 in there, it would be 1/8. If I put a negative 4 in there, it's 1/16. If I put a negative 1 billion in there, it'd be 1 over 2 to the billion power. Is that equal to 0? The only way a fraction can equal 0 is if the top is 0. This top is 1. So 1 over 2 billion, for 2 to the billionth power, holy shit. For any normal person, that would be basically 0. But mathematically, that ain't 0. Because I can still cut that in half, can't I? And get a different number. Well, if it's 0, then it should stay the same if I cut it in half. Have you guys ever heard? All right, I know. I appreciate you for going with me. There's this thing called Zeno's paradox. I didn't bring that up before, have I? You guys ever heard of Zeno's paradox? Okay, stay with me. The first time I heard this, I was such a smart ass, I still am. Zeno is starting off in town A, and he wants to get to town B, but there is no way he can ever make it. Because to get to town B, he has to go halfway, and then he has to go half of that distance, and then he has to go half of that distance, and then he has to go half of that distance, and then half of that distance. He ain't never going to make it. So if I got to go half the way, and then I got to go half the way, and then I got to go half the way, and then I got to go half the way, and then I got to go half the way. I can do that forever. Now this is one of my finest moments. When the teacher told us that for the first time, I said, why not just tell the dude the town is twice as far away as what it really is? So when he goes halfway, he's freaking there. So that was a mistake my teacher made. The real paradox is you can't even get started moving because you say you're going to have to go halfway, but you'd have to go halfway before you could do that. You have to go halfway before you could do that, so it should really be the other way. So he opened himself up for smart ass to step in. All right, I don't know if you guys really are kind of... That's basically what's happening here. Every time I make the power bigger negative, it's another 1/2. Right? 1/2, 1/4, 1/8. I erased 1/8 for some reason. 1/16, so forth, so forth. It's never going to get to 0. What do we call those things that approach something and never get there? Sounds like a math insult. No? Okay. You're all like, math sounds like an insult to me. All right. It's an asymptote. Such a smart asymptote. So let's see what this looks like. So now I know that back here it's going to have to get really close to 0, but never make it there because it keeps getting half closer, half closer, half closer. And I can do that forever. That's the weird thing about having an infinite number of numbers. I can cut it in half and never get to 0. But let's plot what we know. We know negative 2 goes to 1/4. Negative 1 goes to 1/2. 0 goes to 1. 1 goes to 2. 2 goes to 4. So it looks like this. This is an asymptote back there, and that just goes crazy. So if you thought parabolas grew pretty quickly, exponential functions outpace them like crazy. So that's why in horror movies, if you hear that thing's growing exponentially, today it's here, tomorrow it's the United States, and the next day it's the world. That's exponential growth. It just goes crazy. And a little petri dish of bacteria, but they're going to double in so much time. Now there's twice as many, and they're all going to double again. Holy shit, it's overflowing. You're like, dude, I should have not left this sitting out. Okay.
An asymptote wouldn't pass the vertical line test, would it?
So an asymptote is not itself a function. It is an aspect of this. Now why is this a 1-to-1? This function, now be careful, does this ever become horizontal?
That's what I was
It's
thinking.
always getting half closer, so it's always moving. So every horizontal line I can draw goes through once. Our issue is the minute I draw a horizontal line, that is way too thick. I've just drawn through an infinite number of numbers, and that is so freaking. I'm sorry, I don't have to go this direction right now, but I want you to realize there are so many freaking... How many numbers are between this and this? How many numbers are right here? Infinite amount. How many numbers are between this and this? Infinite. How many numbers are between this and this? Infinite. Holy shit. All right, let me stop. That's just going to freak you out. You don't have to worry about it. It's a really good question. I appreciate that because it does look like what I could say here is the slope is becoming closer and closer to 0. But it never gets there. It's never flat. It's always going down a little bit. because it's always getting cut in half. If I zoom in, I can zoom in on this. I might do this one, and then it's going to have a lot of room, right? And then it just keeps going down and down and down. And then I can zoom in on this, and then it's going to go down and down. There's always room, always room. It's crazy. Yes?
So since you wouldn't be able to draw a horizontal line and really be able to tell whether or not it passes the horizontal line
No.
test?
This is what I'm telling you. Functions that look like this do pass the horizontal line test.
Yeah, I get it. I guess what I'm asking is another way to tell if it's a one-to-one function is if its axis of symmetry is y equals x, right?
You have to already have an inverse, and then you can see if they have that axis of symmetry. Does that
Okay.
make sense? Yeah.
Yeah. So you would graph an
Now
inverse.
watch this. I want you to realize something that didn't come up before. Let me see if you guys realize. Every time I try to create one of those things I did earlier, remember these kind of functions?
Yeah.
Do you see how it's got to be always increasing? Or always decreasing? Because what makes it not a one-to-one is if it goes back on its if it turns up, it's not one-to-one. So one way I can tell that this is one-to-one is it's always decreasing, this, if I'm thinking about it this way, right? Or it's always increasing if I think about it that way. Does that make sense? So therefore, any horizontal line will only go through once, because the minute you take another step over, it's up a little bit. If I keep moving this way a little bit, it's up, it's up, it's up, it's up, and then it goes crazy. Maybe. So if the creature is here on Tuesday, it's here on Wednesday, it's up here, holy shit. Maybe. You guys ever heard the thing about would you rather get like $1 million right now or a penny and then I double it and then I double it, right?
Yeah.
So that would basically be 2 to the 30th power of pennies. And if you put 2 to the 30th power, you count there and divide it by 100, that's how many dollars you'd be getting on the last day. So that's a stupid amount of money. Right? Because people don't realize how quickly things grow when I'm doubling or tripling. They grow stupid fast. Maybe. So if I change the base, the basic look. So if I ask you, what does an exponential look like? Draw it in the air. You do this. That's what an exponential looks like. I can move it around like we did before. If I make the base 3, it's going to go up faster and shrink quicker, but it's still going to have that shape. It's like the logo of my little math company. Maybe. So what's really important when you have to graph a bunch of different things is if I know the shape of each of them, the details don't matter as much. I just need a few points and I can put the shape in. When I don't know the shape, I got to do a buttload of points to figure out what's happening. The minute I know the shape of a family of functions, I don't think I've said that phrase yet, a family of functions, because here's the family. Oh, here's the family. That's my horrific rendition of that. Where A is some number. Right, so 3 to the x, 4 to the x, 5 to the x, 6.72 to the x. They all have that shape. Maybe. So let's do another one. You guys take a minute and try to graph this function, and then we're actually going to figure out what its inverse looks like. Go ahead and graph that bad boy. Make a table of values. See if you realize.
How far do you want us to go?
You don't have to use as many points because now we know the shape. So what I normally use, once I know the shape of a function, I just try to pick 3 anchor points. So for this kind of function, I use those as my anchor points.